to make this into e to the x times some e-snack, e-Schlange. Good morning, fellow mathematicians, welcome back to another video. Once again, it's time for, no, not Papa Flammy's random week, but for differential equations. Getting some progress in the series, and today I would like to talk about a special type of ordinary differential equations. Bernoulli differential equations. And those are just some of this form right here, where this power right here, this n, can be element of the real numbers. And I would like to talk about how to solve this kind of differential equation today. I want to consider three little cases. So the first case I would like to consider is when n is equal to 0. Well, what is going to happen to our differential equation? Well, we are going to end up with dy dx plus p of x times y is equal to q of x. And as you might notice, this right here is just a linear non-homogeneous first order ordinary differential equation, and I don't want to go into further detail because I already made a video on how to solve this. So take a look into the description or the playlist. The second case, no, not the third, the second case I would like to consider is when n is equal to 1. Well, what is going to happen to this equation right here? We are going to end up with dy dx plus p of x, y, is equal to q of x times y. And what we can do, we can subtract this term right here on both sides. And what are we going to get? dy dx is now nothing but, and we can factor out this y right here. So this is just q of x minus p of x times y. And right here, I don't want to go into further detail because I made a video on how to solve homogeneous linear first order ordinary differential equations. And if you want, you can call this new polynomial, I don't know, t of x, for example, so that we just end up with y prime is equal to t times y. So we know how to solve this. And now I would like to take a look at all the other n's that could happen. So here's the third case. Case 3. We're going to consider all the other n's. For example, 2, 1/2, I don't really care. So let's take a look at our Bernoulli differential equation once again. So dy dx plus p of x times y is nothing but q of x times y to the nth power. And now I would like to manipulate this equation right here a little bit. So why not get rid of this y to the nth power right here? So how can we get rid of that? Well, we can multiply both sides by y to the minus nth power. So that's something we can do. So this right here is now equivalent to saying we have y to the minus nth power, dy dx, plus, I'm leaving a bit of space here, p of x. And well, this is going to become y to the 1 minus nth power equals to q with respect to x. And it would be absolutely amazing to have this differential equation only in terms of a new variable. For example, y to the 1 minus nth power, let's call it u for example. How can we get that? Well, if we take a closer look here, this nearly looks like we have used the power rule. So, for example, let's take dy squared dx, and since y is a function with respect to x, well, what can we do? We can at first use the power rule right here, so this is just 2 times y, and then reducing the power by 1, and multiplying it by the inner derivative. We have to use the chain rule. And we can use the same procedure up here. So what we really have to do, we have to multiply both sides by 1 minus n. So you see, we are going to drag this new exponent down, just like here. So we want to make this 1 minus n as the new exponent. And also we have to multiply it right here and right here, 1 minus n. So that's something we just have to do. I hope you can see where this thought process came from. And now we can just rewrite this expression right here, this first one, as dy to the 1 minus nth power over dx. You can try it out for yourself. If you differentiate that, you're going to end up with this expression right here. So that's quite nice. So what do we end up with? We now end up with dy to the 1 minus nth power dx plus, and then 1 minus n, p of x, y to the 1 minus nth power equals to q of x times 1 minus n. And we don't want to include the 1 in here. That's why I made a different case, because we would multiply by 0. We don't want that. And just like I said before, let's make a new variable. So let u be equal to y to the 1 minus n, so that it makes calculations easier. So what we end up with finally is just du dx plus 1 minus n, p of x, u equals to q of x, 1 minus n. And we know how to solve that, because this right here, once again, is just a linear non-homogeneous first order ordinary differential equation. So that's quite nice. How is this helpful? Well, let's just calculate an example, for example. So we want to just calculate this little example right here, and it's quite easy. We just want to make use of this formula right here. And if you take a closer look, we would like to multiply both sides by 1 minus n times y to the minus nth power. So that's what we want to do. So we just have to take a look at this power right here. The power is 2, so we are going to multiply it with 1 minus 2 in this case, because n is our 2 right here, times y to the negative 2 power. This is going to evaluate to negative y to the negative 2 power. So that's what we want to do. Now we can multiply both sides under the condition that this isn't equal to 0. We don't want that. We don't want a trivial solution in that case. So we are going to end up with negative y to the negative 2 power dy dx is just, okay, and we end up with negative x in this case. Okay, great. Now we want to make use of this fact right here, that we can transform it like this. So this right here is also equivalent to saying that we have dy to the negative 1 power in this case, so 1 minus n, which is just negative 1, dx is equal to minus x. And now why not let u be equal to 1 over y, which is just y to the minus 1 power. So we end up with du dx is equal to negative x. And we certainly know how to integrate this, or how to solve this. We just have to integrate both sides with respect to x, and then we are basically done. So we are going to end up with integral du dx integrated with respect to x. Well, this is going to evaluate to just u in this case, but what is our u? It's just 1 over y. And also on this side, we have to integrate it. So negative x integrated with respect to x is going to give us negative x squared over 2 plus some arbitrary constant c. So this is negative x squared over 2 plus some arbitrary constant c. And how do we get y? Well, we just have to take the reciprocal on both sides. So that also means that y is now nothing but 1 over. Now we have negative x squared over 2 plus some arbitrary constant c. And this is indeed the solution to this differential equation right here, this one. So that's quite nice. Maybe I'm giving you another example. So this next one right here is really easy to solve in the normal case. You just have to divide both sides by y and then integrate both sides with respect to x, and then you are basically done. But I would like to make use of this new theorem, this new method of solving differential equations. This is quite useful here, so why not make use of it? Okay, so what I would like to do at first is to take a look what our n is. Our n in this case is just a 1, but that's kind of problematic because by this formula we would have to multiply by a 0, so we don't want that. So at first I would just like to multiply both sides by y to the negative 1 power, the multiplicative inverse. So this is like a transformation of this formula right here, Papa's transformation. So what are we going to end up with? We end up with y to the negative 1 power dy dx, and we can rewrite this as 1 over y, maybe that makes it more clear, is now equal to, well, this is going to evaluate to 1. And if you take a look at this right here, which function differentiated would give us 1 over y times the inner derivative, dy dx? Well, this is exactly the natural log. So this term right here can be interpreted as d ln of y, in this case, dx. So if you differentiate that, we have to take the outer derivative, that's 1 over y, and then the inner derivative. Okay, great. And integrating this is quite easy. Just integrate both sides with respect to x. So we end up with this, d ln y. You can also set u equal to ln y, it doesn't matter. dx integrated with respect to x just gives us ln of y. And now the other side, this is the integral of dx in that case, so this gives us x plus some arbitrary constant c. So this is x plus some arbitrary constant c. And now we can use the exponential function on both sides to end up with a solution for y. So y is now equal to e to the x plus c, and we can use the exponential property right here to make this into e to the x times some e snack, e Schlange. This is just some arbitrary constant. And then we are done. So I hope you can see where this came from. This is just my attempt on using Bernoulli differential equations, even on this kind of differential equation. If you did enjoy this video, please like and subscribe and recommend me if you like. If you want to support me a bit more, link to my Patreon is in the description. And up until the next video, have a flammable day. See ya!
Hallo. Ich weiß. Wie fühlst du dich, wenn du Gurke isst?